Newton's second law expressed in terms of momentum. We saw several cases where the momentum of an object changes. In each case, there was a force exerted on the object that caused its momentum to change. We studied about how forces cause motion and Newton's second law of motion in particular in grade 11. Newton's second law of motion states that when there is a net force acting on an object, the object experiences an acceleration in the direction of the force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Vector F equals m times vector A, where m is the mass of the object and vector A is the acceleration of the object. If we observe closely, the velocity of the object changes when a net force acts upon it. In other words, its momentum changes. We can therefore conclude that when a net force acts on an object, its momentum changes. Conversely, the momentum of an object changes only when a net force acts on it. The general form of Newton's second law applies when the mass of an object, such as an accelerating spacecraft, changes. The burning fuel reduces the rocket's mass at each instant of time, so we cannot strictly apply F equals ma in this case. The formula applies only to the special case when the mass of an object is constant. The general form of Newton's second law is stated in terms of momentum. The law states that the net force acting on an object is equal to the rate of change of momentum of the object. This is written as vector F equals vector delta p over delta t, where vector delta p is the change in momentum of the object, and delta t is the time period over which the change occurs. We know that the momentum of an object is the product of an object's mass and velocity, vector p equals m times vector v. If the mass of the object is constant, vector delta p equals vector pf minus vector pi equals m times vector vf minus m times vector vi. This can be written as delta p equals m times vector vf minus vector vi. Newton's second law then becomes vector f equals vector delta p over delta t equals m times vector vf minus vector vi over delta t. We also know that vector vf minus vector vi is the change in velocity, vector delta v. The equation becomes vector f equals m vector delta v over delta t. Vector delta v over delta t is the change in velocity with respect to time, which is the acceleration. This gives the special case of Newton's second law. Vector f equals m times vector a, where the mass is constant.
Starting to feel it? Now go master it with Maski.